Welcome to the MH2801 video segment on a functional argument in the Dirac delta function. So let us recap by remembering what are the two defining properties of the Dirac delta function as a distribution. The first of which is called normalization, and that tells us that the integral from -infinity to infinity of the Dirac delta function itself integrated with respect to t gives us 1. Whereas the localization condition tells us that the integral from -infinity to infinity of the Dirac delta function multiplied by an arbitrary function f of t when integrated over t gives us f of t naught. So these two conditions alone would allow us to evaluate any integral involving the Dirac delta function. Well, almost every. Okay, now consider this particular case. Okay, let us suppose we want to integrate from -infinity to infinity of g of t, some arbitrary function g of t, and then the Dirac delta function. But instead of t minus t naught in the argument of the Dirac delta function, what happens if we have, instead of just t minus t naught, an arbitrary function f of t of the time t? So what is this equals to? Because now there is no t naught for us to see here, and so where should we localize our function g of t? And the answer turns out to be related to the scaling property that we have studied in the previous video segment, but it is a little bit more complicated than that. So we start by talking about the graph of f of t. So let's say we have, no, this is not f of t, clearly. So I need the eraser. Let's erase that, get back my pen, get rid of this, and this is the time axis t. Now, suppose I have the function f of t and say that it looks like this. Okay, so let's say that this is f of t and it has 3 zeros. Okay, it has 3 zeros, x, not x, sorry, t, not x. Okay, let's say this is t1, and then this is t2, and then this is t3. Okay, so the function f of t goes to 0 at t1, t2, and t3. So let's write that down. F of ti equals to 0 for, well, not for all I, but just for I equals to 1, 2, 3. Okay, for I equals to 1, 2, 3, and in these two conditions, normalization and localization, we realize that the localization property requires us to evaluate f of t at the value t for which the argument of the Dirac delta function vanishes. So in this case, if we think that the same kind of thing is going to happen, g of t is going to be localized at those points along t for which f of t is equal to 0, then that will agree with the localization property that we require the Dirac delta function to have, and therefore we can say that if we guess that is the case, then the integral of g of t delta ft, you might think that it is just equals to g of t1 plus g of t2 plus g of t3. So is this true? And the answer is, well, not quite. We're still missing something, and in order to see that something, we have to talk about the Taylor series expansion. Let's say we Taylor series expand f of t about t2. So f of t will be equals to f of t2, okay, plus, what else do we have? We should have f prime of t2 evaluated at t2 times t minus t2 okay, plus f double prime evaluated at t2 divided by 2 factorial times t minus t2 square plus dot 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 dot. Now for the purpose of substituting f of t inside the Dirac delta function, we note that this is 0 because it is at one of the zeros of f of t, and the higher order terms are not important. So the higher order terms are not important, only the linear term is important. So just in the vicinity of t2, what we can say is that the integral, okay, so this integral not from minus infinity to infinity, but just in the neighborhood of t2, you would have g of t times delta times f prime t2 times t minus t2 dt. So what is this equals to? Now if you remember from the video segment on the scaling property of the Dirac delta function, this is a constant, and therefore it plays the role of a scaling factor. And when we do an integration of a Dirac delta function with a scaling factor and an arbitrary function, what we end up with is g at t2 divided by the absolute value of f prime t2. That is what we have discovered when we looked at the scaling property of the Dirac delta function. And now that when we develop the Taylor series of the function f of t about any of the roots, let's say we develop it about t2, we will end up getting gt2 divided by the absolute value of f prime t2. And of course, if we do it for t3, it will look similar, t1 will look similar, so that all in all, the integral from minus infinity to infinity of gt times delta of f of t dt will be equals to g at t1 divided by the absolute value of the derivative, the first derivative of f evaluated at t1, okay, then plus g t2 divided by the absolute value of f prime evaluated at t2, and then plus g t3 divided by f prime, the absolute value of f prime t3. So this is the final answer that we sought when the an arbitrary function is integrated along with a Dirac delta function that has a functional argument.